Thanks everyone for powering through all of these. So I'm going to tell you about ScalarLM today. So over the last 3 years, I've spent a lot of time building multiple iterations of software stacks on top of AMD ROCm. And I want to share a complete stack for training and inference for LLMs. So if you want to know what it takes to run a complete modern application on top of a AMD ROCm cluster, this is running on top of a TensorWave cluster today, you can check out this repo. This is fully open source, fully commercially available, so you can try this out and give it a try whenever you want and read through the source code and see exactly how this works. So beyond the existing applications, we've also started looking at what comes beyond LLMs and what comes beyond the current generation of models. So I'm going to talk about that a little bit and tell you about some of the design decisions that went into this framework, and then tell you a little bit about the framework. Okay, so my belief for a long time has been scaling laws, has been that by training these models on larger amounts of data, they're going to keep getting smarter. This was our paper from Baidu in 2017 where we introduced scaling laws. And these have been the driver of all of the progress that we've seen today. This is the 𝗚𝗿𝗄𝗏𝗺's keynote slide about OpenAI's progress in scaling laws. The idea is that by following a simple recipe of making the computer faster, the models keep getting smarter and they can keep solving additional tasks. And my belief is that the future beyond scaling laws is actually scaling faster than scaling laws. So you'll probably notice in the modern generation of GPUs, especially the AMD GPUs, they've started to add additional capacity. So my belief is that systems that have additional capacity will be able to take advantage of much larger neural networks that can scale faster and learn even faster than scaling laws. So this is an example of what a LLM can do today. This is written by Claude 3.5. This is a full React app. This is a maps app that was generated from data. It has tabular data. It has drop-down menus. It has 4 different panels, and this was rendered entirely by a web browser running this 2,000-line React app. So this is an example of what LLMs can do today. But if we extrapolate forward with scaling laws, either we scale faster or we just follow scaling laws for the next 10 years, we should be able to solve much harder problems that have a much higher level of complexity. And these are going to get us from these medium value use cases to very high value engineering use cases. Things like writing complete system software, developing new drugs, building entire database pipelines, not just 100-line queries, but several thousand-line data pipelines, and building AI applications themselves, like building autopilots. So my belief is these things are going to be enabled. And in order to do that, we're actually going to need a new type of algorithm. So the new algorithms that are going to scale faster than scaling laws are going to be kind of like DeepSeek R1. So the previous generation of models was heavily oriented on chat. They would look at what the user typed in, and then they would complete the sentence. They were autoregressive models that would complete the sentence. So DeepSeek R1 is a step towards super alignment, which is what I'm calling a new kind of model that can learn faster than scaling laws. So these models do reasoning. When the user asks it a question, the model, before it answers the question, will first spend some time doing inference. So it will think about the answer. It'll generate reasoning tokens where it tries to figure out the right way of answering the question, and then it answers the question. So from a software infrastructure perspective, these models are starting to require not just training for training foundation models and not just inference for evaluating our models. They're starting to do inference first to think about what the right thing to do is, and then based on what the correct answer actually is, whether the model got it right or not, they're doing backpropagation. So they're doing training. So we're seeing emerging algorithms that scale faster start to take advantage of both training and inference. And that's why we built ScalarLM, which is the first machine learning framework that includes high-performance training and inference together into a single framework. It uses Megatron Core, the training stack from Megatron Core, which normally doesn't run very easily on AMD, but it's been ported to AMD. It uses the model library from Hugging Face, and it uses the inference engine from VLM. And it unifies them all together into a single framework that runs out of the box on ROCm. So this is an example of a snapshot on TensorWave on a 8 MI300X GPU server that's training a 70 billion parameter model using a fraction of the memory. So it can fit about a 400 billion parameter model. So this can train serious big models today. This is just a comparison of how does ScalarLM fit into the ecosystem. The biggest thing is that it has both training and inference together. We don't think that this exists even in the NVIDIA ecosystem. And secondly, it has mainline ROCm support. So out of the box, you don't have to have a separate build. You just build the normal containers, and it'll run on MI300. OK. This is the Llama stack. This is Meta's perspective on what you can build on top of this layer. So this is just another way of thinking about how this fits into the ecosystem. These are some of the types of capabilities you can build on top of a framework like this. So you can build agents. Obviously, you can build inference. You can build post-training. You can build evals. You can connect it to memory-augmented systems like RAG systems. So this layer really sits at the lower layer, providing a train endpoint, so the ability to train models. As soon as models are trained, they're immediately deployed. So if you've taken a reasoning trajectory and you've generated a reasoning example, you can immediately send that to backprop, and then backprop will produce a new model, which can immediately be served from the inference engine. So you can write loops that are going to call training and inference in a loop, for example, to perform reinforcement learning. So we can do training. We can also do inference using the normal OpenAI client interfaces for inference. Okay, and this is just giving you a little bit more details of under the hood, how the different pieces are put together. As I mentioned, the entire thing is completely open source. This is a CC0 license, so should be available for absolutely any commercial use you can think about. This is our v0.5 release, so it's fully functional. You can run it today, as I showed, running on an MI300 cluster. We're going to do a performance-oriented release in a few months, and our very interesting community feedback. Thanks.